Hello class, week 6 guided notes. We will be talking about more operations involving the whole numbers. The whole numbers again are 0, 1, 2, 3, etc. And the operations we're going to focus on this time are multiplication and division. Number 1, the quantitative operation of multiplication is the mental act of combining some number of copies, or you could say groups or iterations, of some quantity. Quantitative multiplication is conceptual and can be imagined even with unmeasured quantities. In contrast to quantitative multiplication, we have numerical operation of multiplication, which is the combining of a specific number of copies of one numeral to form a new numeral. Let's consider the following statements. Number 1, combine 3 copies of John's money. So we have John's money. I'll do a little circle to represent all of John's money, or you could do a box or a column or some sort of representation that this is John's money. When we do 3 copies of it, I do copy paste. And here's 3 copies. I've sort of drawn them overlapping, but here's the 3 copies of John's money. We don't know how much money it is. Let's just put some sort of a dollar sign in here. And you combine them into a new amount. And so this collection here combined is 3 copies of John's money. And I can imagine that without even knowing how much money John has. We could even keep 3 general and just sort of imagine this idea of just copying until I've copied a certain number, right? I just wanted to specify 3 so I could say when to stop the copying. But you can imagine multiplication without even knowing how many copies you're doing exactly. Combine 3 copies of John's $4. So now we have a little more specifics. So now let's do a dot to represent a dollar. So there's John's $4, we'll say. And then we just copy and paste. And we're going to do 3 total copies. So we actually copied twice, if you want to be technical, but we have 3 copies of it right here. And so this would give us a total of $12 if you were to count it out. Combine 3 copies of 4. So this is going to be similar, except now we have, I call these contextually empty or vacuous numerals. We're doing what I also refer to as naked math, just math with numbers without specifying what the numbers represent or what their units of measure are. But 3 copies of 4. So you have 4 somethings, and I'll use the dots again, and we want 3 copies of that. So there's 2 copies, and there's 3 copies. And you can imagine making 3 copies of 4, and you get 12 something. Now the numerical operation of multiplication would be something like this. You're probably familiar with this notation. 3 times 4 equals 12. And this means 3 copies of 4, and that total is 12. The quantitative operation is a conceptual operation. That was more, this is very conceptual, just this idea of copying and combining a certain amount. This one here is the numerical operation of multiplication, and this one's sort of a blend. We're doing numerical calculation, right? We did 3 times 4 to get 12, but we also have this, we have something to imagine. We have dollar signs, and I can imagine John having $4 and then copying that 3 times and combining it. So there's definitely something to imagine to be coupled with the numerical operation of 3 times 4. Notice that for multiplication, the 3 values involved, 2 are in the operation, and the third is the result of the operation, all have different reference. The value that represents, so let's take a look at this. If we were to say, let's do this context here where I do 3 times 4. So we have 3 copies of, and then it's $4 per copy is $12. So there's 3 different values represented here. One is how many copies we have. One is how much of something we have per copy. In this case, it's money and measured in dollars. So 3 copies, $4 per copy, and then the final result of this operation is $12. You could say $12 total or $12 as a result of the copying. And all of them have subtly different reference, different units. 3 is number of copies, 4 is dollars per copy, and 12 is just dollars. So the ones that are most similar are the 4 and the 12, because they both refer to dollars, but the 4 has the extra distinction of that's $4 per copy. And the 12 does not have that distinction. But otherwise, the 4 and 12 are both referring to money and both referring to measured in dollars. All right, back to our statement here. The value that represents the number of copies is called the multiplier. So in this case, that would be the 3. The value that represents the amount of stuff per copy is called the multiplicand. So that would be the $4 per copy, right? That's the amount of stuff per copy. And the value that represents the resulting amount of stuff is called the product. And that would be the $12 in this case, would be the product. And for numerical multiplication to produce consistent results, the product and multiplicand must have similar reference, with the distinction that the multiplicand is an amount per copy. That's what I was saying here a moment ago about the 4 and 12 have the same referent. They're both referring to dollars, but the 4 is a dollar amount per copy, where the 12 doesn't have that distinction. Continuing with our reading here, for each phrase below, express the situation as a multiplication statement in the form multiplier times multiplicand equals product. Identify the reference of each value, then express the statements in multiple ways, both in writing and in speech. Okay, so we have 2 cartons with a half dozen eggs each. So this would suggest that we have 2 cartons. This is one value with unit, times, we're doing a multiplication statement. The multiplier would be the number of cartons. The multiplicand is the amount of stuff per carton. So there's going to be a half dozen eggs. So we have 6 eggs per carton. The multiplicand, this position here, will always be something per something, even when you're just saying per copy like we did up here. It's a good way to think of the multiplicand as always something per something. And the result of this operation would give us the total number of eggs. If we have 2 cartons and 6 eggs total, then we have 12 eggs. All right, so we've expressed this as a multiplication statement, and we've identified the reference of each value. And you can see they're all different. Cartons, eggs per carton, and then just simply eggs. But again, the multiplicand and the product both refer to eggs, at least, with the distinction that the multiplicand is a per copy, in this case per carton. So sometimes copies are just, there's nothing to visualize when you think about copying something. It's like copy and paste, copy and paste. Sometimes there is a physical representation of a copy. Like I can imagine a carton. That's something I can think about. And inside that carton, I can picture the 6 eggs. And so then when I look at the final result, you know, if you put I'm going to draw a box to represent a carton and dots to represent eggs. So here's one carton with 6 eggs, and here's a second carton with 6 eggs. This is a multiplicative relationship because, and one way to think about this is because I can think of this in 2 different ways. By this, I mean the total amount at the end. I see that as either 2 or I see that as 12. It depends on what unit I'm looking at. So if I'm looking at that and I want to justify that 2 is what I see there, then I would say I see 2 cartons. Or if I want to think about that in terms of eggs, how many eggs do I see in that big box? I would say I see 12 eggs. And so we have this idea that 2 is equal to 6, which is a weird notion. But if you put units on it, then you can see why they're the same amount. Because this would be 2 cartons. Get rid of that. 2 cartons corresponds or is equal to 6 eggs. Now conceptually, cartons and eggs aren't the same thing, so when we're talking about this equal sign, we're being a little bit loose about its interpretation. Maybe instead of an equal sign, we can do a correspondence arrow that connects these two things. This communicates that 2 cartons corresponds to 6 eggs. But the ability to see a singular amount as 2 different values, depending on what your unit of measure is significant as we move forward in our quantitative reasoning, especially when fractions will show up. And just keep in mind, we do this all the time that you're comfortable with. For example, if you were to measure something as 2 feet long, someone might say, well, I measured that and I got 24, but my unit of measure was inches. Like 2 feet and 24 inches correspond to the same length. And 2 cartons and 6 eggs correspond to the same amount of eggs in this case. So just something to think about. It says, express the statement in multiple ways, both in writing and in speech. So in writing, let me leave the units off and just write this statement. 2 times 6 equals 12. I just want to show that there's other ways to imply multiplication when you're working with 2 numbers. Sometimes you'll see a 2.6, and this also means multiplication. Sometimes you'll see a 2 and then like an asterisk 6. This should also be interpreted as multiplication, unless otherwise stated. Sometimes you'll see a 2 in a parentheses and then a 6 next to it in parentheses. This also means to multiply the 2. Or if one of these is not in parentheses but the other is, and then we default to assume that we're talking about multiplication here as well. So a variety of ways symbolically to get this idea that we have 2 copies of 6 eggs per carton per copy, and we get a total of 12 eggs. Let's see, different ways to say this in speech. I could say 2 groups of 6 eggs makes 12 eggs. 2 cartons of 6 eggs per carton make 12 eggs. 2 copies of 6 eggs make 12 eggs. 2 iterations of 6 eggs makes 12 eggs. You could also, the word we say here sometimes just times. So we say 2 times 6 equals 12. So there's a variety of ways to get at this idea that we're doing a quantitative operation / numerical operation of multiplication. The next one is 5 cans with 3 tennis balls each. And if you recall the cans of tennis balls, the tennis balls are stacked in the cans like this, and then we have 5 of such things. All right, so I'll just paste 5 of these things here. Okay, so you can look at this total amount. If someone says, hey, what do you see here? Some of you might say, I see 5 things, and those things are 5 cans. And another person might say, I see 15 things, and those 15 things are tennis balls. So this idea that 5 cans corresponds to 15 tennis balls establishes this multiplicative relationship between these 2 items. But if we were to write this out, it'd be something like this. 5 cans with a unit times, I'll do the dot this time, but we say times, or multiplied with, or multiplied by. There's a few ways you might say that. 3 balls per can. Again, the multiplicand is a something per something. Gives me a total of 15 tennis balls. Okay, let's move on. Number 2, the operation of multiplication is numerically commutative, although it is not conceptually commutative. Consider the following phrases. What is consistent and inconsistent about each? Okay, so we have 3 buckets with 2 gallons of water each. Okay, so I'm going to picture, 3 buckets, and then there's 2 gallons in each. I'll just say 2G in each. 2G, 2G, 2G. And so I see a total of 6 gallons total. This is suggesting that when we have 3 buckets, and we multiply, I'll do the asterisk this time, by 2 gallons per bucket, that we get a total of 6 gallons. Or the resulting amount is 6 gallons. In the second scenario, we have 2 buckets with 3 gallons each. So this time we have, maybe bigger buckets, but there's 2 of them, and they each have 3 gallons. So imagine these are the same. Okay, so I'm going to essentially just copy this sentence but change some numbers around. Now we have only 2 buckets, but there's 3 gallons per bucket, but we still get a total of 6 gallons, right? If that's what we're after. So this says, what is consistent and inconsistent about each? Well, what's consistent is the total amount of water. The result of the operation is 6 numerically in both cases. We have 6 gallons in each scenario. What is inconsistent about each? Well, physically, these are different scenarios. They both represent the same total amount of water in the end, but having 3 buckets with 2 gallons in each is not the same thing as having 2 buckets with 3 gallons in each. And so we say that conceptually, if we're going to insist, when you have multiplication, I'm going to, maybe I didn't make this clear earlier, I'm going to make it clear now. I'm always going to let the first number be the role of the multiplier. And the multiplier is the word we're using for the number of copies. The second number in my multiplication will always be, for me, the multiplicand. And that's always the amount of stuff per copy. And then C is the result, or the product. We call it the product officially. But we're going to be consistent in insisting that the first number is the number of copies. So when you see 2 times 3 in naked math, don't think this means 3 copies of 2, because that's reading it backwards. Interpret this as 2 copies of 3. If you want to do 3 copies of 2, then switch it around. Now, in both cases, numerically, you're going to get 6. But visually, conceptually, if we insist that the first number is the multiplier, we do not have similar imagery. Right? In this case here, I'm picturing 2 copies of 3, and that's how I get the 6. And here I'm picturing 3 copies of 2, and that's how I get the 6. Right? So this one corresponds more with the first example, and then this one here corresponds better with the second example. So they're inconsistent. By they, I mean these 2 scenarios, these 2 visuals are inconsistent in the sense they don't produce the same visual, but they are consistent in the sense that they both yield a result of 6 gallons in total. All right, so this is what I mean when I say that multiplication is numerically commutative, because when you sort of take the context out of it, 3 times 2 and 2 times 3, you get the same result, and you get 6. But I don't consider them to be conceptually commutative because 3 copies of 2 is a different visual than 2 copies of 3, even though they both yield 6 items. The operation of multiplication is associative, both conceptually and numerically. Consider the phrase below. So we have 2 classrooms with 4 tables in each classroom, and each table has 3 seats. Okay, so let's do a visual of this. I'll just do one classroom. There's 4 tables in it. I'll do little boxes in there for the tables. And each table is 3 seats. So I'll do a dots for the seats. Okay, now we had 2 of these, so I'm going to just go ahead and copy and paste this. So here's 2 classrooms with 4 tables in each classroom, and each table with 3 seats. There is a multiple operations of multiplication happening here. For example, let's say we have 4 classrooms. I'll just do CR for classrooms times, I don't know why I said 4. We have 2 classrooms. 2 classrooms times 4 tables, I do capital T per classroom, times 3 seats, I do S per table, 3S per T. This sort of has the flavor of having 2 different multiplicands because they're both rates. Notice a table per classroom and a seat per table. And 1 multiplier, 2 classrooms. Now, if you were to figure out how many tables we had first, in other words, do this calculation, we would get a total of 8 tables. And then we'll times that by 3 seats per table. And if I have 8 tables and 3 seats per table, then I get a total of 24 seats. Right, and that was us multiplying these together first. Okay, I'm going to do something similar. But I'm going to multiply first these amounts and see what happens. And see if we get the same result. All right, so we have 2 classrooms, 2 CRs. Now, if I do, there's 4 tables per classroom and there's 3 seats per table, then I can multiply 4 and 3 and get 12 seats per classroom. Which is exactly what you see if you look at, per classroom, how many dots are there? There's 12. We have 12 seats per classroom. And now I can multiply, let's put some equal signs to connect these things. Now I can say 2 classrooms times 12 seats per classroom will give me a total of 24 seats. All right, so it didn't really matter which multiplication I did first. Let me shrink this down a little bit, and this as well. The conclusion is that with multiplication, if you have 3 things being multiplied in general, and this is numerically and conceptually, that you can do the first 2, A times B, and then times C, or you can do A after you do B times C. So do B times C, get a result, and then do A times that result, and you get the same result. Because it doesn't matter which ones you do first, you can just write this without any parentheses because it's open to the reader to decide which multiplication they want to do first. Okay, and then this idea, let's go back to the numerical commutativity. If multiplication is commutative in the sense that if you just think, forget about the context, just A copies of B produces the same amount as B copies of A. So these wind up being the same numeral when you switch the order of the multiplication. Even though I don't think of the same thing when I think of A copies of B when I think of B copies of A. So I say it's conceptually not commutative, but numerically it is commutative. I hope that makes sense. Let's look at number 3 here, next page. Numerical multiplication can be modeled using the grid approach. We're going to model the operation below using a grid, and we're going to use the grid to demonstrate that multiplication is numerically commutative. So 4 times 7. We're going to do something like, by grid approach, we're going to say we're going to have 4 rows, and we're going to multiply that with 7 boxes per row. Or we can say 7 columns per row. So by the grid approach, we would have, I'm just going to make a box first. Okay, and imagine we have 4 rows, and each row has 7 columns. So I got to make 7 columns in here. And I'll do my best to make these look kind of all the same, but it's okay if they're not exactly identical. But we have 4 rows and 7 columns. And when you do 4 times 7, you're asking yourself how many little entries are in this grid, right? And you can count them out if you wanted to. We have 1, 2, 3, 4, etc. And you're going to get 28 total. So let's just say that there are 28 squares in our grid. All multiplication of whole numbers can be modeled this way. Think of it as a box, as an area, and you're finding out how many squares are in that box. If it's 4 units one direction and 7 units the other direction. And so when I have 4 rows, 7 columns, instead of writing rows and columns and all that, you could say that we just have 4 copies of 7. I like this brief way to think of multiplication. When you see that dot or that times symbol, the X or the asterisk or whatever, you just put the word copies of there. So 4 copies of 7 is how I read that. 4 is the multiplier and 7 is the multiplicand. And those 4 copies of 7, well, each row is a 7. Right? So you could say, I'll use the highlighter, yes. Okay, so we have, there's 1 copy of 7. There's a second copy of 7, right? A third copy of 7, and a fourth copy of 7. And when you put those 4 7s together, you get this 28, which actually introduces the idea that you can think when you're doing multiplication of whole numbers, you can think of multiplication as doing some sort of repeated addition. So you have 4 copies of 7 added together, right, and that gives us the 28. But if you look at the table as far as counting columns, right, here's, oops, wrong, use the highlighter. Here's 1 copy of 4, 2 copies of 4, 3 copies of 4, 4 copies of 4, 5 copies, 6 copies, 7 copies of 4 will also yield the same amount. So if I switch this around and say, hey, this means 7 copies of 4, that's like adding 4 to itself 7 times. Oops. Try to write 4, but say a 7, and I wrote a 7. I think there are 7 4s there. Yes, we get a total of 28 with that approach as well. So the grid is very helpful because you can crisscross through it. You can be thinking of, well, here's 4 copies of 7, or you can think of this as 7 copies of 4. And the grid is helpful for showing that multiplication is numerically commutative. In the end, we're talking about 28 squares here. Because numerical commutative multiplication is commutative, the multiplier and multiplicand are considered interchangeable. So they're often just referred to as factors. Now I want to be careful moving forward. These are considered the factors of 28, meaning that when you multiply 4 and 7, you do get 28. And it doesn't matter which order you do it, right? 7 times 4 also gives you 28. But I only ever use the word factors when I'm doing the naked math, when I'm not thinking about something. As soon as I start thinking about something, including even a general statement like 4 copies of 7, then 4 has taken on the role of the multiplier, and 7 has taken on the role of the multiplicand, which is the thing being copied, and the multiplier is how many copies. 4 copies of 7 is a different visual than 7 copies of 4. So when you want to get down to that idea that one number represents copies, the other represents amount of stuff per copy, then I'm more comfortable identifying what the multiplier and multiplicand are, and not just calling them factors, because factors is too general. It doesn't tell me which ones I should think of as the multiplier and which one I should think of as the multiplicand. Of course, you're free to switch which ones you think of as the multiplier and multiplicand and still get the same final result, but they are different visuals that lead there. It's like 2 different ways that take you to the same destination. Eventually, a learner will practice multiplication with numbers between 1 and 10 to the point where they can correctly and quickly and sensibly, I mean they could justify why 4 times 7 is 28, but they could also fill in this table quickly and correctly with the products a times b, where either factor can be considered the multiplier. So here we're doing a times b. Let's assume a is the multiplier, because that's our traditional approach, is to assume the first one is the multiplier. And so that would mean that this is trying to say we have one copy of 1. Right? And we put that into this entry. 1 copy of 1 is 1. Then we have 1 copy of 2. Well, that's just 2. Right? Let's fill in a random entry. Let's go 4 copies of 7. That makes 28. But you can also read this table backwards. If you want, you could assume b is the multiplier, although I would discourage this. If you're going to assume b is the multiplier, then write this down instead. Right? You want to build a habit where whatever you're thinking of as the multiplier comes first. just for consistency's sake. But mathematically, we could just say that B is the multiplier and A is the multiplicand. But I will resist that, and I'll try to avoid ever doing that. I want to think of the first number in a product always as the multiplier. But you could do this backwards. Like I could think of this 8 as being the multiplier and this 3 as being the multiplicand. Right, so to get this entry right there, I would say 8 copies of 3. That winds up making 24, etc. You get the idea. I'm not going to fill in this whole table, but you should be able to do that pretty quickly with accurate numbers. I just pick one more random one. Here's 9 copies of 5. 9 copies of 5 will wind up making 45 when you're done. And you might get to the point where you just simply have this times table memorized, which is good for efficiency's sake. But if you forget an entry, like this one here, I just happen to forget. What's 6 times 7? I don't remember. But 6 times 7 means 6 copies of 7. So you just add 7 to itself, 6, so add 6 7s together and you get 42. So you have the ability to reproduce an entry in the case you just forgot it. Your memory has failed you. In your guided notes that you turn in, make sure you just go ahead and fill in this whole table, just for practice. Number 4, model the following phrase with a grid, with base 10 blocks, and with a place value table. So we have 3 buses with 16 students each. Okay, we'll say that's a bus, and there's 16 students in each. So I'm going to go ahead and just put in dots for a student, and I think I haven't done enough. Let's put 4 more. So I did in groups of 4. Yeah, we have 16 there total, and here's a bus, and we have 3 such things. Okay, so right now I'm modeling this with a way I did not require in our instructions, but it's always helpful to be able to picture this in multiple ways. Right, this is a bus, so we have some wheels, etc. If you want to actually imagine actual buses here. Okay, but we're going to model this scenario. Buses would be the multiplier, because we have 3. Each bus is like a copy of something. Then we have 16 students per bus. I'll just put a B for bus. And we're going to wind up getting a total of 48 students. I'll let you count them out to verify. I mean, that's how a student might do this initially, is just count them out and see that we have 48 students total. But we're supposed to model this with a grid, so we're gonna do a grid that's 3 by 16. Okay. So now I'm gonna cut that in half. We want 3 rows. Each row is gonna represent a bus, essentially. Okay, so this will be bus 1, bus 2, bus 3. And now I want to divide this into 16 columns. So I have to divide each of these in 8, half, half, half. I think this will make 8 right there. Yes, it does. Cut in half, 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 cut in half. There should be 16 columns and 3 rows in this. And this yields, of course, 48 squares, which each square will represent a student. So I'll put ST for student. So this is how we modeled it with a grid. We're going to model it with base 10 blocks. So if I'm going to represent 16 students with base 10 blocks, so we're going to have a 10 piece, and then I'll use dots for the 6 students. So here's one way you might arrive at the 48 initially, other than just counting them out in a grid. And I'm going to do 3 copies of this because we have 3 buses. And then just push all this together. Right? So we're going to have, initially we have this going on. And now we want to group these things, try to make another 10 out of students. Doesn't really matter how I do this, but there's 10 students right there. So that's going to form another 10 base 10 block. So we'll now have 1, 2, 3, 4, and that last one is the red one that I created from the red boxed students, and then there's still 8 students accounted or left over. So, here's one way that we could take our 3 copies of 16 with base 10 blocks and just figure out that we wind up with 48, right? 48 total students. Also a place value table, right? So if you're going to do a place value table, this will be the 1s and the 10s. All right, so we had 16 students to begin with. I'll use dots. And actually, let me make the table have a little more space that way. So we had 1 10 and then 6 1s. And that represents the 16. But now we're going to copy this. So I'm just going to copy this, and paste it right here in the same table. And so now you can sort of see the three copies of the 16. And then we do something similar, right? We look for, if I erase these horizontal lines and think of this as a single place value table now, well, we want to take 10 of these dots and make one more dot over here, right? So this winds up yielding a place value table that has 4 dots total, including the red one I'll put as the new one that we just entered. And how many are left over here? Well, we had 6 down there, and then the extra 2 that weren't in the red box there. Right, so you can model this with place value tables too. Number 5, consider the operations below and model them with a place value table. Consider the first number as the multiplier. Okay, well, that's going to be generally our default assumption, is that the first number in a product is the multiplier. So we have 10 parentheses 23. So the implication is we're doing 10 copies of 23. So we have in the place value table, 23 is 2 10s and 3 1s. And then we're going to make 10 copies of this. So let me erase the table for now. Let me do the copies first. So there's 2 copies, 3, 4, 5, and I'm just going to copy this all once more. Okay, so now here's our new place value table with all these dots, right? We had 23 and I copied it 10 times. Well, because I copied it 10 times, let me throw an extra row here in our box. We'll move that and shrink it down a little bit. The original dots that represented the 23, let me make them a different color. Let's say they were orange, were the original dots. And so we see a total of 10 copies. But if you were to now gather them, because we did 10 copies, if you were to gather them this way, right, those 10 dots, including that first orange one, become a single dot in this next row over. And then these 10 dots become a single dot in the next row over. Well, these 10 dots here will move over to the next box this way, etc. You're getting the idea, I think. That's going to go to that box, and that's going to go to that box. So in the end, the result is going to be, after I do 10 copies of 23, a student will learn that, okay, let's see what happened. I'm going to need a total of 3 boxes in my place value table. The 2 columns in the 10s became dots in the hundreds area, and the 3 columns that used to be in the 1s position became 3 dots in the 10s position, and then there's nothing left in the 1s position. Oops, didn't mean to do that. Every now and then my thumb hits one of these arrows down here in the bottom right. So this shows, helps a student realize that when you multiply a number by 10, you just simply shift the digits left in place value table, all the digits. So then the final result, so 10 copies of 23 will yield 230 of something. If you do 100 copies, well, you do 100 copies is the same thing as doing 10 copies and then 10 copies of that, copying 10 twice. Or you do 100 copies. If you start with 17, 17 would look like this initially. And you do 100 copies. Well, if you do 10 copies of this 10 here, that's going to make it into 100, but then 10 more copies of that will advance it over 2 spots. So you're going to wind up really with a shift this direction, and a student would spend certainly more time wrestling with this than we're doing right now, but this will wind up going over 2 places in our place value table, and these will go over also 2 places. Right? In the end, suggesting that when you multiply 17 by 100, you're still going to get a 1/7, but you need the 1/7 shifted over 2 spots each in the place value table. If we do this one, 12 copies of 1,000, right, remember we're assuming that the first number is the multipliers, and so I put the 1,000 last this time. So 12 copies of 1,000. Well, here's 1,000. Oops, so that's 100. I need 4 entries in my place value table, right? The ones, the tens, the hundreds, and the thousands. So 1,000 would be a single dot right there. And we want to do 12 copies of that. Okay, so I'm going to just copy it right now, 12 times. Let's say the original is going to be orange again. So let's pretend that was the original. And now I need a total of 12 copies of 1,000. There's 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Oops. Now I'll make the place value table. Okay. So I started with 1,000 and I did 12 copies of that. Well, that just made 12 dots in the 1,000 portion of our table, and we need to group 10 of them. So I'll do the original dot, and the 9 below it will become a single dot in the next entry over. Right, so this will yield a result that has a table that has 5 place values. We have a single dot moved over that I'll make it red, and that's the one that moved. And then the 2 extra dots still here. And so you can see, as far as place value tables are concerned, that we have a total of 1 10,000 and 2,000s. So we have 12,000 essentially. Will be the results of doing 12 times 1,000. Anyway, we're going to generalize this work above and describe how to compute a product where either factor is a power of 10. So it really just boils down to this. You take any number, 23 for example, multiply it by a power of 10. Let's go with 4 zeros. You're going to wind up getting 23 and then just tack on 4 zeros. So in this case, 230,000 is what it yields. And it doesn't matter if you're doing 23 copies of 10,000 like we are doing here, or if you say something like, let's do 100 copies of 62. That gives us 62 with 2 extra zeros, which is 6,200, right? Multiplying a number by a power of 10, so like a 1 with so many zeros behind it, just puts that number of zeros after the number that is the other factor. So in other words, multiplying by powers of 10 turns out to be rather straightforward in our decimal system. Just tack on more zeros. Use a grid model for multiplication to justify the following claim. Okay, so we have 3 times 6 is equal to 3 times, and I just decompose 6 into 2 plus 4. And now the claim is that I can do 3 times 2 and then add that to 3 times 4. Okay, Okay, so let's do a grid model for 3 times 6. I want 6 columns and 3 rows. So 3 rows and then 6 columns. Well, 6 can be decomposed into 2 and 4. And notice that we're going to get a total of 18 out of this. Right? We have 18 is the result of 3 times 6. Let's write it like this over here. 3 times 6 will yield 18 items. 3 copies of 6 items gives me 18 items. And the copies are the rows, right? So I'm thinking here's one copy of 6, a second copy of 6, and a third copy of 6, and we'll have a total of 18. Well, you could decompose that 6 into 2 and 4, right? So I can effectively split my table into a collection of 4 columns and 2 columns. So it should make sense that I can arrive at 18 the following way. Do 3 copies of 4 and get that part of the table, and then to that add 3 copies of 2. And if I do 3 copies of 2, and you can do that in reverse order too. I could do 3 copies of 2 and then 3 copies of 4, because I decompose this as 2 and 2 plus 4, but I sort of put the 4 first here. But it really doesn't matter, because addition is commutative. And so we have 3 copies of 2 is the orange, right? 3 copies of 2 is the orange, and that gives me 6. 3 copies of 4 is the green, that gives me 12. And then we add these together, we get 18 total, right? Okay, so this one here is the orange boxes we counted, and this one here is the green. Same thing can be true for subtraction. 3 times 4, well, we know that 3.4, 3 times 4 will give us 12 somethings. We can model that pretty easily. 3 copies of 4. Let's do a grid to represent this. So there's 4 columns and 3 rows, right? So we can count out the 12 items. Well, I can express 4 as 6 minus 2. So this is not really it's a decomposition in a way. It's not really breaking 4 into 2 pieces that when added together make 4, but it's expressing 4 as the result of doing 6 minus 2. And this is claiming that I could do 3 times 6 and then do 3 times 2 separately. So if I tacked on 2 extras, right, to make a total of 6 columns, remember my goal is to arrive at this amount. But if I begin with 3 times 6, right, 3 times 6 is 18, and I'm going to remove from that 3 times 2, which is 6, and we can say remove the 6 from the 18, and we get 12. All right, so I started with this 18, and then I removed this 3 times 2. This portion of the block got removed. I think I just say, oh, gone. And that leaves what's left here was just 3 times 4, which is 12. Okay, so the statements above can be generalized, and they are known as the distributive property of multiplication. Since multiplication is numerically commutative, the distributive property can be expressed in many ways, as depicted below. So here's our general idea of A times B plus C can be expressed as AB. And by the way, if you have 2 letters next to each other, you don't need to put an operation in between. The default is that it's multiplication. You know, normally you'll do A dot B. Sometimes when it's letters, we don't like doing AXB because it looks like X is just another letter. Is this 3 letters, or is X a times symbol, right? So it gets confusing when you're working with letters. That's why we sometimes like the dots. And if we're really lazy, just get rid of the dot. Right? If you put A, B next to each other, then we're assuming that you mean multiply them. And then plus AC. And the other one that we can generalize above was that A times the difference can be expressed as A times B minus A times C. Now, because of the commutative property of multiplication, you can actually, switch these around as your starting point and say that we have B plus C first and then times A, and then the distribution can happen the other direction. It could be written as AB plus CA. I'm keeping the A's on the left because the A's are on the left here. But if we take context out of this, there's just so many different things you can do here. The distributive property looks like the A just multiplies to both pieces. As we say, it distributes. A distributes to both of these pieces, and you can also distribute from the right side to both pieces. Right, is what we're seeing here. Same thing for a difference. So I just put a plus minus, and this would be a plus or minus, depending on what the case was. But because of the commutative property, you could then say that this is the same thing as AB plus or minus CA. Just commute one of them. Or you could commute both. AB plus or minus AC. Right? There's just a lot of different ways that you could express the commutative property, the distributive property, because of the commutative property. But the ones that are most often presented it's summarized typically this way. A times B plus or minus C is equal to AB plus or minus AC. Knowing full well that you could switch these around, and if it's addition in here, you could even switch the B and C around. Be careful, if it's subtraction, you can't do that. You can't. This one's not true. That A times B minus C is the same thing as A times C minus B. That one's not a true statement because subtraction is not commutative. So just be careful about that. Okay, so here's usually how the distributive property is written. There are several strategies for multiplying multi-digit numerals, such as decomposition and distribution, and also using the standard algorithm. Calculate the following operation in multiple ways. Okay, so we're going to do 23 times 15. One way I could do this is to say that I'm going to do 23 times 10 plus 5 to get a 10 involved, and then distribute. So now I can say, well, that 23 times 10 is easy. That one's 230. And then I want to do 23 times 5. Well, I'll do another decomposition. Right? 230 plus, and change 23 into 20 plus 3. And multiply that by 5, and then distribute the 5. So we have 230 plus 20 times 5, 25s, or 5 20s, whichever way you want to think of that, is going to be 100. And then 3 5s or 5 3s will be 15. And so in the end, we can say that we get a result of, we're going to add 100 to 230, that's 330, and then add 15 to that, and we get 345. Okay, let me just show you the standard algorithm that you're used to seeing. 23 times 15, something like this. I'm sure you've all been taught this at one point. I'll show you what's truly going on here when you do this. All right, we do the 5 times the 3 first, and you get 15, but you only put the 1 spot here, and you carry the 1 from the 15 up to there. Then you do 5 times 2, and you get 10, but then add that 1, you get 11, and you write that 11 right there. Then you start with 1 and multiply that to the 3, and that just gives you 3, but you put it below the 1 position, which is the tens position. And then you do 1 times 2, and you just get a nice 2, and then you get these entries. And then you add them up column by column, and you get 5, 4, 3, 345. Now, if you're comfortable with doing this process to get 345, that's great. It makes you a very efficient calculator. Although calculators are more efficient than you are and also more accurate than you are. But what's the mathematics truly going on behind this process? Because it feels very magical. I mean, you should never teach how to multiply multi-digit whole numbers to a student by only teaching them this algorithm, because it makes mathematics something that's inaccessible to them, some list of rules they don't understand that they have to follow. What's truly going on here is the following. we are doing decompositions. I am expressing 23 times 15 as distributing a bunch of things. I'm going to write 23 as, well, just keep 23 as 23, but we'll write 15 as 10 plus 5, and I'm going to distribute. So you have 23 times 10 plus 23 times 5. Then each 23 I'm going to decompose and then do more distributing. So 23 is 20 plus 3, and that'll be all times of 10. And then we have 23 is 20 plus 3, and that'll all be times of 5. Okay, now I'm going to distribute again, right? The 10 will distribute and the 5 will distribute. So we have 200 plus 30. And over here we have 100 plus 15. And we just add all these things together. We get 345. The algorithm that you see here is you could argue, is a more efficient way of doing this. However, the algorithm here is less sensible than doing this. Right? So you have this trade-off. You get more efficiency, but the process makes less sense on the surface when you do the standard algorithm. Compare these. When I did 5 times 3 and got 15, that was like me doing this 5 times 3 right there. And then when I did 5 times 2, that's actually 5 times 20, right? Because that 2 is in a tens position. So I did 5 20s, and I got a total of 100. That is where I got this 100 from. And when you did the carrying the 1 over, that was just breaking up the 15 into 5 and 10, and adding that 10 to that 100. So 110 plus 5. You got this 115 out of doing that. Then I shift gears to this 1. That's not really a 1. That's actually a 10. I'm doing a 10 times 3 when I do that, which is happening right here when I did that product, 10 times 3. Then I did a 10 times, not 1 times 2, but 10 times 20. That's what gave me that 200, right? The 10 times the 20 gave me that 200. And then I put the result down here, but notice because it was shifted over and there's a placeholder of a 0 there, then when you did the 10 times 3, you got 30, and the 10 times 20, you got 200. You combine those, you have 230. So then when you're actually adding these together, you're actually adding not 115 without the 0 there, it looks like you're adding 115 and 23, but in a weird way where the 23 is lining up with the 2 1s instead. It feels like magic, but there's no 23 here. There's 230 that's happening here. This 230 is being added to this 115, and we get that 345. So really, when you're doing this algorithm, you're doing a whole bunch of distributing and decomposing and putting pieces back together to reconstruct an answer. That's how the algorithm was born. Okay, let's move on to the next item, division. Now, there are many ways to characterize the meaning of division, but in my judgment, the quantitative operation of division is best thought of as an operation that resolves either a missing multiplier or a missing multiplicand multiplication task. Express each mathematical statement below as a worded question, assuming the first factor is a multiplier. I'll keep writing that to be clear, but in general, that's our assumption. Also provide a specific context that would elicit each question. All right, so we have 3 times question mark equals 12. And we're going to phrase this as a question. This would read, since 3 is the multiplier, and we know it, we would say 3, and to be general, let's just go with copies. 3 copies of, and then we don't know, of what equals or makes or results in, we'll say makes 12. Right, here's our question. This is called a missing multiplicand task. We're trying to figure out the amount per copy such that 3 copies of it would make 12. The next one would be, well, this time it's the multiplier we don't know. So we don't know how many copies. So we might say this, phrase this one as how many copies? How many copies of, we do know the multiplicand, it's 3 per copy, make 12. Okay. So these are called missing multiplier and missing, the first one's missing multiplicand, and this one's a missing multiplier. And they're conceptually different questions. Now let's try to think of, so division is the operation that answers these questions. And so we would do, we would say this symbol here, we would say 12 divided by 3, and we'll put the result there in a moment, but that division operation is the operation you do to the 12 and 3 to find the missing multiplicand. It turns out that you can also do it over here, do a 12 divided by 3 to find a missing multiplier. Let's think of a context next of each question. 3 copies of what make 12. All right, let's say we have 3 baskets. And we don't know how many eggs per basket. We don't know. But we do know that there are 12 eggs total. Right, so this would be a context that would elicit this kind of question. We have 3 baskets, so 3 copies of what amount of eggs per basket will give me 12 eggs total. So the number of baskets is the multiplier, the question mark is the multiplicand, and the 12 is the product. Over here, how many copies of 3? So this would be like we don't know the number of baskets. So we say, I don't know how many baskets I have if we want to go with the baskets and eggs. This time the baskets only have 3 eggs per basket. That part we do know, but we know we have 12 eggs total. And our goal here would be to figure out how many baskets. Now the answer in both these cases is going to be 4, but the 4s are very differently interpreted. Numerically, if you were to reach for a calculator, you would do 12 divided by 3 in each case. Right, so numerically, you do the same operation. This division operation is an operation we use to solve a missing multiplicand or a missing multiplier multiplication task. We use the operation of division to do that. In one case, the 4 is going to be eggs per basket. In the other case, the answer is 4 baskets. So the interpretation of the 4s are very different. Okay, let's go ahead and read what we're seeing here. In both cases above, we use the symbol 12 divided by 3, which is read 12 divided by 3, to represent the operation that resolves the task. In both cases, the numerical answer is 4. However, the quantitative meaning of the 4 is different in each case. In other words, the 4s have different reference. This suggests that there are 2 fundamentally different ways to think about division. So when you're given a naked problem of division, 12 divided by 3 and 12 divided by 3, in both cases the answer is 4, but you think differently to arrive at that numerical answer of 4. In one case you're asking yourself 3 copies of what make 12, and the other you're asking yourself how many copies of 3 make 12. And those are very different things to resolve. Let's look at the table that we have here. So we have a multiplication statement, A times B equals C. Again, we are assuming that the A is the multiplier. So that's the number of copies. B is the multiplicand. That's the amount of stuff being copied. And we're calling C the resulting amount, also called the product. Okay. All right, the 2 types of division. Type 1 is called partitive or sharing division. It's where you know C and you know A and you're trying to find B. Right? So if you know C and you know A and you reach for a calculator and you do C divided by A, you're going to get this answer of B. The A, B, and C in this statement correspond to the same A, B, and C in that statement. So this is the operation you would do if you're trying to resolve a missing multiplicand task. Right? In other words, we're trying to find B because we don't know B, and B is the question mark. We're missing the multiplicand. If we don't know B, we're trying to find it, so we would do C divided by A. And so when you type C divided by A, it answers this question. A copies of what amount make the amount C, right? Kind of exactly what we saw up here. This was a missing multiplicand question. It's an example of type 1 division, which is also called partitive division or sharing division. Let's say that instead, you know the multiplicand and you know the product, but you're trying to find A. That's analogous to this situation, where we know how many eggs per basket, we know how many eggs total, but we're trying to figure out how many baskets there are. That's like trying to find the multiplier. It's a missing multiplier task. But you still do division of the two things you know. You still do the C divided by B in order to arrive at the A, where we're trying to find A. And this resolves a missing multiplier task, this kind of division. It's called quotative, by the way, or measuring division. And C divided by B represents an answer to the question, how many copies of the amount B make the amount C? Right? How many copies of 3 make some other amount? Now, concerning the operation of division, the first number is called, in the operation, is called the dividend. So when you actually see the division symbol like this, like here, then we actually have some more names for these pieces. The first number is called the dividend. The second number is called the divisor. And the resulting number is called the quotient. Now that's true in both cases, because these names sort of exist independent of a context. Oops. When you just reach for a calculator and you do C divided by whatever, a number divided by a number equals another number, then the first number was the dividend, you divide the dividend by the divisor, and then you get an answer that's called the quotient. Okay. So let's see, we're down here again. We just finished reading up to this point, so let's read now right here. As you can see above, for each type of division, the dividend corresponds to the product. So notice in both cases, the dividend was C, and C was the product in the multiplication context. However, for the first type, the divisor corresponds to the multiplier, and the quotient corresponds to the multiplicand. So the divisor was A, which is the multiplier, and the result of the division operation was B, the quotient, and that corresponds to the multiplicand. Whereas for the second type, reading right here now, for the second type, the divisor corresponds to the multiplicand, and the quotient corresponds to the multiplier. Now it's really easy to get lost in this mess of terminology, and it's just easy to get lost in this. It's maybe better to think that the two types of division are the, if you want to name them this way, partitive division is you're trying to figure out how much per copy. This is the general high-level question. How much per copy? That means you're trying to find a multiplicand. And the second type is you're trying to figure out how many copies. You're trying to find a multiplier. So I've seen some textbooks, characterize these two different meanings for division as the how many copies and the how much per copy meanings for division. And if it gets confusing, just go back to this simple example here where you have a 3 and a 12, and again a 3 and a 12. And in each case, the 3 was one of the factors, but it changed roles, right? In one case, the 3 was the multiplier. The other case, the 3 was the multiplicand. And we were trying to find the other factor. And they produce very different looking questions and very different problem-solving skills to arrive at answers. Number 9. So, is the operation of division commutative and or associative? Let's investigate this. Consider the operations below and think about both the partitive and quotative meanings for division. Okay, so when you see 6 divided by 2, there's two questions you can ask. One is, how many copies of 2 make 6? Right, so here's 2, maybe I'll just use dots for it. Here's 2, and if I'm going to start making copies, how many do I need to get to 6? And you're like, oh, look at that, 3 copies. 1, 2, 3. 1, 2, 3. So we have 3 copies of 2 make 6. This is the quotative. I'll just put the quotative meaning modeled here. How many copies of 2 make 6? The other meaning is the partitive. So that's where we know we want 2 copies of something to make 6. All right, so we know that there's going to be 2 copies, not 3 copies this time, and we know that we want to, so we have 2 copies of what amount makes 6. We know the total amount needs to be 6. So this is why it's also called the sharing meaning, because you're saying, okay, well, if you have 2 copies and we have 6 total, it's like saying you have 2 kids and 6 candies, and kids understand this pretty well, and you want to share it. So you start just handing out the candies until you've handed them out fairly to each person. And you realize, okay, I've now handed out 6 candies to 2 people, and each kid got 3 candies. This is the partitive, or the sharing meaning of division. And so in one case, 6 divided by 2, let's put a line here, 6 divided by 2 gave me an answer of 3 copies. Because we were saying 2 copies, how many copies of 2 make 6? In the next question, we were asking ourselves, 2 copies of what amount make 3? And this is 3 stuff per copy. We're going to have units here. Maybe 3 candies per kid, for example. 3 stuff per copy. And they're very different visuals. But numerically, in both cases, the answer is 3. It's just the meaning of the 3 changes depending on what we're thinking about. 2 divided by 6. This is like saying you have 2, if we do the partitive meaning, this is like saying you have 2 candies but 6 kids, and you want to say, okay, 6 copies of what amount will make 2? Well, this is going to involve fractions. The answer is going to wind up being 1/3, and since we haven't formally talked about fractions, we'll talk about this later. We'll just say more later on this. But the idea is that we don't get the same thing as 3. So this tells us that division is not commutative. We'll see more on this later. But this is all we need to really see is to know that division is not commutative. It does matter the order in which you do the division. You can't switch the role of the dividend and divisor and get the same quotient. Now let's investigate associative ideas. So here's just a double division. Let's first do this where I put the parentheses here to suggest we do that division first. So we get 16 divided by, and then 4 divided by 2. Either way you think about this quotatively or partitively, the answer is going to be numerically 2. And then when I do 16 divided by 2, again, either way, if you think of this quotatively or partitively, you're going to get a numerical answer of 8. Well, let's consider what would happen if I did the same divisions, but in a different order. Consider this order instead. So 16 divided by 4 numerically will produce a 4. And then we have to divide that by 2. And 4 divided by 2 numerically gives me 2. We don't get the same result. So it does matter the order in which you do the division when there's a string of 2 divisions in a row like this. And so we know that division is not associative. So it's not commutative or associative. Let's go to number 10 here. For the operation below, invent a situational task that would elicit a partitive model for division, and then another task that would elicit a quotative model for division. Then resolve each task and draw an image to support each answer. All right, so this would be a little bit similar to what we just did up here for the 6 divided by 2, but let's go with the partitive first. Partitive meaning, or the sharing meaning. So let's back up. If you're still not sure what that word means, then think, okay, here's the question that we want to be answering by this division when we're doing partitive. Partitive corresponds to the missing multiplicand. So we know how many copies, but we don't know how much is in each copy. So when I go down here and I want to do a partitive interpretation of 28 divided by 4, the question I'd be asking is 4 copies of what make 28. Okay. Well, let's give a situation now. Let's add more complexity to this by giving a context. So let's say we have each copy is, if we want to do the basket and the eggs idea again, let's go ahead and just do that. So we have 4 baskets with how many eggs per basket, or you can put a question mark here if you want 4 baskets of a question mark eggs per basket make 28 eggs. Okay, so now we've invented a context, and I will leave it to you to actually write this out as a word problem. Like, you know how many baskets there are, you know how many eggs you have, the question is how many eggs are there per basket. And we are assuming that the number of eggs per basket is consistent, right? It's not like you have 4 baskets and you have 10 eggs here and 8 eggs here and 5 eggs here and 5 eggs here. This would also give you 28 eggs, but we're making an assumption that we want, when we use the word copies here, right? These are not copies of each other because they're different. Well, these two are copies of each other, but we're trying to find one thing so that when all 4 of these are the same, hence the word copies, then we get 28. So we definitely don't want a case where we have different numbers of eggs per basket. So 4 baskets of how many eggs per basket will make 28 eggs. All right, there's lots of ways to do this. Some students will take, the 28 eggs, whatever. They'll draw the 4 baskets like this, and then they'll start sharing them. They'll say, okay, here's 1 egg, put it in there, right? This egg, put it in there. This egg, put it in there. And then you keep this up until you've distributed all the eggs evenly. Now, hopefully everyone will get the same amount of eggs. Otherwise, we're going to have to break some eggs up and give people portions of eggs to make it fair. But since this unit is on division with only whole numbers, then we're going to expect only whole number answers. We'll do fractions later. So I'm going to, as my representation of this, I'm going to do a box like this where each of these boxes represent one of the baskets. And I have a total of 28 eggs. Well, start handing them out like cards. So there's 4 eggs spread out to the baskets. There's 8 eggs accounted for. Right, there's 12 eggs accounted for. 16 eggs accounted for. 20 eggs accounted for. 24 eggs accounted for, and then 28 eggs accounted for. And then once you have it fair sharing, you can see that there are 7 eggs per basket. Numerically, if we did this on a calculator, we would just have said, hey, 28 total eggs divided by how many baskets I have, and it would give you a 7 to interpret that as how many eggs there are per basket. And this would be a partitive scenario. Okay, let's do the quotative scenario next. All right, back up to our table here. Quotative is our division. We wanted to answer a question like, how many copies of the amount B make the amount C? So this is where you know the multiplicand and you know the product, but you don't know the multiplier. So as a general question, I would say, okay, how many copies of 4 eggs, or we'll just say of 4, we'll make a context here in a moment, of 4 make 28. Okay. Oops, I'm going to run out of space a little bit. Let me shrink some of this down so I can raise that up and give myself a little bit more space. Okay. So if we invented a context here, then this would be like, okay, we don't know how many baskets there are, but we do know that there's 4 eggs per basket, and we know that there's 28 eggs total. So this would be a good situation where we would have to do division, and this time we would be making baskets of 4 eggs per basket and counting baskets. So a good way to do this one is to I'm going to write out all 28, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28 eggs. There they are. And we know that there's 4 eggs per basket. So we can start saying, okay, well then there's a basket worth of eggs. Here's a second basket. Right? Here's a third basket. A fourth basket. A fifth basket. A sixth basket, and perfectly we have 7 total baskets. Right, so this concludes that we have 7 baskets. And numerically, I still would have done a 28 divided by a 4 and got a 7, just that the interpretation of the 7 is very different. Right, in one case, we were trying to find how many eggs there were per basket. In the other case, we were trying to figure out how many baskets there were. They both use the same numerical operation of division, but they're both very different conceptually, and the meaning of the answer 7 is very different. Number 11, there are a variety of strategies for performing numerical division involving large numbers, including decomposition and the standard algorithm. Calculate the following operation in multiple ways, including using the algorithm. Okay, so we're trying to do 147 divided by 7. If I want to think partitively, then I'm thinking that we know the number of groups. So there are 7 groups or 7 copies. So let's do 7 boxes. Oops. Let's make that a little bit more narrow in the middle. And then thirds. So there's my 7 copies. And we want a total of 147. Well, I don't want to do 147 dots. So let's just start splitting things by numerals. Let's say I do, let's split up, 70 is easy to split up into 7 groups, because there would be 10 per group. Right? So let's put 10 in each group. Let's do another 70. I'm trying to account for everything, so let's put another 10 per group. Right? So just putting numbers in these boxes instead of dots. And that's 140 accounted for. We only have 7 more. Well, that's perfect. We can put 1 more in each box, right? And that should get us there. That accounts for 147 items fit into 7 copies. And we can see that we have 21 per copy. 21 items per copy, which confirms that 147 divided by 7 is 21. And I used a partitive meaning to do that. The other is to do a quotative meaning and think, okay, well, how many 7s make 147? Right, so let's write that question. Let's put here, this is the partitive interpretation, and now I'm going to do a quotative interpretation, which is how many 7s make 147. Okay, so let's just start doing groups of 7s until we get close to 147. Let's do 10 7s. Here's 10 7s. That makes 70. So what's left? We'll remove 71 from 147. We still have 77 left. Well, if I do another 10 7s, that makes a total of another 70. So remove 70 from this, and we have 7 left. Well, now we just need 1 more 7 to get the rest of it. And then now we have left nothing. So let me just count how many 7s total I did. And I just realized that, look at that, I did 21 7s makes 147. So the answer would be 21 copies. 21 copies of 7. Okay, I'm writing kind of big here. I want to do let me shrink that down a bunch, give myself room to do the algorithm. The algorithm, you've learned that you put the 7 over here on the side, and then a 147. The algorithm is actually very much like the quotative meaning here. You're just counting 7s and seeing what's left after you've done so many. And you might remember doing something like this. Does 7 go into 1? The answer is no. So then think of this as 14. Even though that's not really 14, it's 140. Does 7 go into 140? The answer is yes. It goes in, well, 7 goes into 14 twice, but really when you put the 2 there, you should really, what's really happening is that you're doing a 20. You're saying, okay, 27s makes 140, and remove that and see what's left. You're like, oh, just 1. So then you put a 1 here. Now most of the time the algorithms say don't put the 0 there, put the 1 next, and then do 1 times 7, you get 7, remove, and you have nothing left. So you've accounted for everything. So you say, okay, 21 sevens is what it took to make 147. But I don't like just putting a 2 there and thinking of that as 14. I'd rather think of, I'm not asking how many times does 7 go into 1. I'm asking how many times does it go into 100. I'm not asking how many times does 7 go into 14. I'm asking how many times it goes into 140. And the answer to that is really 20. You should really put a 20 here. 20 times 7 is 140, right? That's what gives the extra 0 right there. And when you subtract that, most of the algorithm normally would say don't put a 0 here and don't put a 0 here. Just subtract the 1, 4 and the 1, 4 and then bring that 7 down. And it all feels very magical, like number soup is happening, and students don't really understand why this works. It's because we're being lazy. We're not putting the zeros here. That really make this make more sense. 20 times 7 is 140. I remove 140 from 7, from 147 I mean, and I get 7. And then I just need one more 7 will give me this last 7 to remove to get 0. Right? Well, you don't even have to do 20. Technically, you could do this in groups of 10, kind of like I did up above, and still do the long division algorithm. You can say, hey, what happens if I do 10 sevens? 10 times 7 is 70. Remove that from 140, we get 77. We'll do another 10 sevens. 10 times 7 is 70 again. Remove that from that, and we get 7 left. Now we just need one more 7, and remove that, and we're down to nothing left. And then you just combine all those and say, okay, 21 copies of 7. Frankly, I prefer this way of doing the long division algorithm because it puts all the zeros where they belong, and it makes the numbers make more sense. It doesn't feel so magical to a student. Whenever I do it is possible also to do the traditional algorithm for long division like you see here with a partitive meaning, but I kind of like the quotative meaning where you're just asking yourself how many 7s make 147, you just do that in waves until you get to 147. Okay, one more picture here, number 12. Each task below suggests a multiplicative relationship. Characterize each task as either a missing multiplier, missing multiplicand, or missing product multiplication task. Express the multiplicative relationship with a question mark in the appropriate position. Include reference on your values. Indicate whether multiplication, partitive division, or quotative division resolves the task. Perform that operation and give your answer with the correct reference. State any assumptions we had to make to resolve the task. All right, so lots going on here. Frances has 18 candies and 2 friends, and she wants to share her candy with them and herself. How much candy does each person get? All right, so we want to express this as an A times B equals C, and which of these 3 pieces do I know? Well, we know that there's 3 friends, counting herself. And we don't know, we're going to multiply this with, we don't know how many candies per person. But we do know that the total is 18 candies. Right, you see this multiplicative structure with a missing multiplicand. We know we have 3 friends. We don't know how many candies each person's going to get. As soon as you see each person get, then we know it's a candies per person that we don't know, and that's the role of the multiplicand when you have that rate, something per something, and we know the total amount is 18 candies. All right, so we've characterized this. This is a missing multiplicand task. Let me make this a little bit smaller and zoom in here a bit. All right, so we're going to say this is a missing multiplicand task. That looks like multiplier as well, so I better spell it out. Multiplicand task. That's the first one, first set of instructions here. Express the multiplicative relationship with a question mark in the appropriate position and include reference on your values. We did that already. indicate whether multiplication, partitive division, or quotative division resolves the task. Well, to resolve the task, to get the question mark, right, we want to do division. We want to do 18 divided by 3. And the division that we do is the partitive or quotative? Well, partitive is when you know the multiplier but don't know the multiplicand. So this is an example of doing partitive division or sharing division, right? Sharing is called sharing, I think, for the obvious connection that you have 18 candies and 3 people and you're trying to share them equally between the people. So partitive / sharing division is what's going to solve the task. And then 18 divided by 3 will wind up being 6. So we're going to get 6 candies per person. And that was, I think, our last thing we had to do was to say, perform the operation, give your answer with the correct referent, which we did. 6 candies per person is our answer. And then state any assumptions we had to make to resolve the task. Well, we did assume that it was fair sharing. So we did assume that each person gets the same amount. But it is possible to share the candy with 3 people, but in unequal ways. But when we do division, we're assuming that we're doing it in equal ways. Because however much candy each person gets is what we want to copy. When you copy something, you create an exact copy of it. Number B, Ricardo can make 5 baskets in an hour. How many baskets can he make in 3 hours? All right, so 5 baskets in an hour, that's a per hour situation. That's a multiplicand. It's a 5, we'll say B per hour, 5 baskets per hour. And we want to do 3 copies of that because he's working for 3 hours. So this is a situation where we would be multiplying 3 hours times 5 baskets per hour, and we would get a total of 15 baskets. Or that, actually, we don't know that yet, so this is what we're after. Right, how many baskets can he make in 3 hours? So here's our multiplication statement with a question mark in the right position. This time it's in the position of the product. So this is a missing product problem. And to resolve it, the question mark is we do numerical multiplication of 3 times 5 and get 15. Right, so we use multiplication to resolve it. That's how you resolve any missing product tasks. You just do multiply the 2 factors. Multiply the multiplier and the multiplicand, and you get the product. And 15, I should have said how many baskets. Let's put a unit on there. 15 baskets. And what did we assume on this one? Okay, we assumed that Ricardo was not taking any breaks, right? We were assuming that he worked at the same rate for each hour. So we assumed that he could make the same number of baskets each of the 3 hours. The same number of baskets each hour. So he didn't slow down, for example, or take a break or whatever. That he just worked 5 baskets each hour. And the last one, there are 14 gallons of water in a barrel. 1 scoop can remove 2 gallons at a time. Ooh, so I see this statement right here is a 2 gallons per scoop. That is a multiplicand. It establishes a relationship between gallons and scoops. How many scoops will it take to empty the barrel? Well, we know the total amount is 14 gallons. So the question is, how many scoops? And this is our multiplicative structure. How many scoops times 2 gallons per scoop will give me the 14 gallons total? Well, this is a missing multiplier task. Missing multiplier task, which suggests that we can resolve it through division. We do the quotient divided by the multiplicand, the product divided by the multiplicand, which in this context, the 14 is now called the divisor, and the 14 is called the dividend, and then the 2 is called the divisor. But we do know that we're going to wind up getting 7 and then scoops, right? That's the unit here. And what flavor of division was this? This was our quotative division. also called measuring division, because in a way you're sort of like saying, you've got 14 gallons, I'll represent that way, and each scoop is 2 gallons, and you're trying to figure out how many of these make the bigger one, and the answer is 7 of them, right? It's like you're measuring the 14 gallons in units of 2-gallon scoops. That's why it's called also the measuring division. But this was definitely a situation where we're trying to figure out how many copies. When your division means how many copies of something makes something else, that's quotative or measuring division that's happening. And what assumptions did we make here? We assumed that each scoop was full, right? That he didn't do partial scoops or anything. Like, assume each scoop removed its capacity. We'll assume each scoop removed 2 gallons. Okay, and that wraps up our Week 6 guided notes on multiplication and division involving whole numbers.